In this module, you will learn about the algebra of limits and calculate the limits of polynomial and rational functions. If the functions are well defined, then the limits of the sum, difference, product and quotient of functions can be found easily. Let's see how. Let f of x and g of x be two well-defined functions, and limit x tends to a, f of x and limit x tends to a, g of x exist. Then, the limit of the sum of the two functions is equal to the sum of the limits of the functions. We will verify this theorem. Let f of x be equal to x square and g of x be 3x square. Now, we verify according to the theorem for x tends to 1. First, we will find the limit on the left-hand side. Now, we verify the right-hand side. We can see that the left-hand side is equal to the right-hand side. The limit of the difference of two functions is equal to the difference of the limits of the functions. Let's verify this theorem with the functions shown with limit x tends to 1. The left-hand side is equal to -2. The right-hand side is also equal to -2. Hence, the theorem is verified. The next theorem states that the limit of the product of two functions is equal to the product of the limits of the functions. Let's verify the theorem with the functions while x tends to 1. First, we will find the limit on the left-hand side. Now the limit on the right-hand side is as shown. Since the left-hand side is equal to the right-hand side, the theorem is verified. If f of x is a constant, then we can write the relation as shown. The fourth theorem is that the limit of the quotient of two functions is equal to the quotient of the limits of the functions. Here, the denominator is not equal to 0. As in the previous theorems, these can be easily proved using the functions shown. We can see that the theorem is verified. Now, we will see the limits of polynomial functions. Based on the theorems that we have discussed, we will see how we can find the limits of the polynomial functions. A polynomial function is defined as shown. If f of x is a well-defined function, then limit x tends to a, f of x is equal to f of a. Let's substitute the polynomial in place of f of x. We can assume that each term in the polynomial is a function. Therefore, right-hand side can be written as shown. The first function is a constant. The second term also follows directly. The third term can be considered as shown. Similarly, the limit of the final term in the polynomial is as shown. This sum is equal to f of a. Now, we will see the limits of rational functions. A function f of x of the form g of x divided by h of x is called a rational function. Here, g of x and h of x our polynomial function. If we wish to find the limit of the function as x tends to a real number a, then we have these cases. A case where h of a is equal to 0 and g of a is not equal to 0. In this case, the limit does not exist. Another case is where both h of a and g of a are equal to 0. In this case, the limit takes the indeterminate form. In this case, we will remove the factors of x minus a from the numerator and the denominator. We can write the numerator and the denominator as shown. Here, two cases are possible. Either q is less than or equal to p, or q is greater than p. For case 1, the limit becomes 0. This is the determinate form. The limit does not exist for q greater than p. Let's try to understand the discussion by finding the limit of the function as shown. When we find the limit turns to be indeterminate. So, to avoid this, we write the numerator and the denominator in the factors of x minus 3. The limit is equal to 1 divided by 27. As a culmination, we will discuss a theorem on the limit of a function as shown. Here, n is a positive integer. We will prove the theorem. The numerator can be expressed as shown. Now, the limit can be expressed as shown. Now, the limit of this function can be found just like we find the limit of a polynomial function. This limit exists even if n is a rational number and a is positive. For example, look at the limit of this function.